I want to talk about the relationships between rectangular, cylindrical, and spherical coordinates. I've listed here all the relationships we've already written down between rectangular and cylindrical coordinates, and I've plotted a point in space, and I've labeled the distance r from cylindrical coordinates, the distance rho from spherical coordinates, and then angles phi and theta, which together come from spherical coordinates, but theta is the angle from cylindrical coordinates as well. And I'm hoping that this diagram is going to help us figure out the rest of the relationships. Well, one relationship I want to write down right away. This point, rho away from the origin, that means it lies on a sphere of radius rho. So x squared plus y squared plus z squared has to be equal to rho squared. Rho's positive for us in spherical coordinates, so we could also think of it as being this, which more naturally arises from the distance formula. Well, if I put that together with x squared plus y squared being r squared, I could write that as r squared plus z squared equals rho squared. And I actually see that in this right triangle. There's going to be a right angle here because that's rising straight out of the xy plane, where I have r, rho, and then that would be the z coordinate. That would be the height above the plane. So this is just the Pythagorean theorem, and that nice happy right triangle. Okay, let's see if we can figure out a relationship between r, that distance in cylindrical coordinates, and converting it into understanding it in spherical coordinates. So I'm wondering what r is equal to. So this time I want to imagine that instead of thinking of r as here, I draw a distance straight back to the z-axis, and if I stay parallel to that ray, that distance will also be r, and I'll also be in a right triangle. It's like I've taken this triangle and flipped it upside down, but the nice thing about that is that phi is in that particular right triangle. And so if I take sine of phi, I would get r over the hypotenuse, which is rho. And so r is equal to rho sine phi. So there's a nice relationship that relates things in cylindrical and spherical coordinates. If I wanted to convert a spherical point to cylindrical, I could certainly think about that. But it also lets me write down a new relationship for x and y that would convert from rectangular straight to spherical, because x is r cosine theta. Well, x is r cosine theta. Well, r is rho sine phi times cosine theta. So I'm just substituting that in. I need to do it again. So rho sine phi times sine theta. Okay, so new relationships here, right? So we have some new things popping in. And let's see what else we can say. Let's see if we can write down a relationship for z, relating the z coordinate from either rectangular or cylindrical coordinates to spherical coordinates. Well, I can come back to this right triangle because I see the z coordinate here. Well, if I take the cosine of angle phi, it would be it would be z, the adjacent side, over rho. And so I would get z equals rho cosine phi. And here are all of the relationships between rectangular, cylindrical, and spherical coordinates.